Hey everybody, welcome back. It's Mr. G. What we're going to be doing today is Tech 101 Test 2 Review. So we've got our trusty formula sheet, and here's what we're going to be looking at as far as topics in test number 2. So the first topic we're going to be looking at is series parallel combinations. Then we're going to be looking at maximum power transfer. And then the last we're going to be looking at is Thevenin's theory. And again, this is all in prep for test number 2. So let's take a look at series parallel circuits, shall we? In series parallel combination circuits, as the term describes, it is part series and part parallel. So if we had a circuit that looked like this, with 1K and 2K, and we'll call this one 3K and 3K. If we were to solve for this circuit, we'll call that R1, R2, R3, and R4, and we'll say it's 12-volt supply. So hopefully it's obvious at this point in time that this circuit is made out of components that are in series and some components that are made in parallel. And the two combine to be a series parallel combination. When you're solving circuits like this, the first thing you have to look for is finding R total. Because R total will then give us I total, and then we can use I total, and we can work our way through the circuits to calculate voltages and currents and things like that. But the main focus to start would be this thing called R total, so the total resistance of this circuit. So in order to do that, we have to identify how this circuit simplifies. Now, we know from our formula sheets and things that we've done before that there's two ways to calculate R total. For a series circuit, it's R1 plus R2 plus R3, etc., etc., etc. For a parallel circuit, it's 1 over R1 plus 1 over R2 plus 1 over R3. Neither one of these formulas will work by themselves when you have a series parallel combination. So what you have to do is simplify the circuit so that one of these formulas will apply. So what we're going to do is we're going to examine the circuit. And the first thing I always suggest is mapping the total current in the circuit. So the total current will leave the source and travel. It goes through that resistor, comes here, then splits, rejoins, and then flows back to the supply. That's the path of I total. So that means that this current goes all the way through that resistor and that resistor. So that means they share the same current. These two things are going to be in series. Then it splits here, and we have a branch here and a branch here. those two branches are in parallel. So when we look at it, we can say the first obstacle that the current encounters is this. We'll call that A. Then the current encounters this obstacle, which is B. Then the current encounters this obstacle, which is C. And those obstacles happen at different times. First it goes to this one, then to this one, then to this one. That makes these obstacles in series. So our total in this case would be the resistance inside bubble A plus the resistance inside bubble B plus the resistance inside bubble C. Now what we want to do is we want to break down what's inside each bubble. So in this case, resistance A, the bubble A, all that's in there is one resistor at 1K. So one resistor at 1K plus bubble B. Inside bubble B is just this one resistor at 2K. So 2K plus whatever is inside bubble C. Now bubble C is 3K in parallel with 3K. So when you have 3K in parallel with 3K, that comes to 1.5K. So inside that bubble is actually 1.5 kilo ohm. So our total in this case is going to be 1 plus 2 plus 1.5. So it's 1, 3, 4.5. So 4.5 kilo ohms is our total. Then we can go ahead and find I total. Solving for I total, we know is V total divided by R total. V total is 12 volts. R total is 4.5K, 4.5. Therefore, I total is 12 divided by 4.5 kilo equals 2.667, so 2.667 milliamps. So we know that the current leaving the source is 2.667 milliamps. That current flows through that resistor. So therefore the voltage across that resistor is the current going through it times the resistance. So the voltage of R1 is going to be equal to 2.667 milliamps times 1K, and that is 2.667 volts. Voltage of R2. The same current flows through that resistor, so we end up with 2.667 milliamps times 2K. Ohm's law, 2K. And then we're going to end up with 5.3, so we'll say 2.667 times 2, 5.334. 5.334 volts. And that's the voltage across that resistor. So now we have the current going through that one and that one. We also have the voltage across this one and this one. Now we're here. There's many ways to figure this one out. We know that this resistor is 3K and this resistor is 3K. So we can take the total current and it's going to split evenly down these branches. So 2.667 is going to give us 1.33. Or if we wanted to, we could use the voltage divider, and the voltage divider is going to be the resistance of C, that bubble, which is 1.5K. So we're going to say that the voltage across R3 is equal to 12 volts, and then multiplied by this resistance, which is 1.5, over R total, which is 4.5, and the voltage across R3 and R4 together is going to be 1.5 divided by 4.5 equals times 12 equals 4 volts. So if there's 4 volts across this resistor, there's 4 volts across that one. So voltage across R4 equals 4 volts as well. And then we can use Ohm's law and we can get the current. So 4 divided by 3K is going to give us 1.333. 4 divided by 3K gives us 1.33. And if we have 12 volts at the source, we know that this drop is 2.667, so 2.6677 plus this drop as 5.334 plus the drop of C, which is 4 volts, and we do that, that's going to equal 12. So that's Kirchhoff's voltage law that says that this voltage plus this voltage plus this voltage is going to equal to the total. Another type of series parallel circuit would be something that looks like this. We can say this is 1K, and this is 2K, and this is 2K, and this is 1K, and this is going to be 3K, and this will be 9 volts. Again, if we're going to solve for all of this, we're going to need to find R total so we can get I total. R total, again, we only have these two formats, so we have to figure out which one of these formats does this R total simplify to. So in this case, when we look at the current's going to split, 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 and rejoin, rejoin, and rejoin. So basically this point to this point, this point to this point, and this point to this point puts this branch in parallel with this branch in parallel with this branch. So we have branch A in parallel with branch B in parallel with branch C. So you can actually do 1 over the resistance of branch A plus 1 over the resistance of branch B plus 1 over the resistance of branch C. Inside A, I have 1K and 2K giving me 3K. So this becomes 1 over 3K plus 2K and 1K gives me 1 over 3K plus 3K, 1 over 3K. And if we plug that into our calculators, we're going to find R total in this circuit is equal to 1K. Then we have Ohm's law that's going to tell us that 9 volts divided by 1K is going to give us 9 milliamps. So again, this current is going to be 9 milliamps. And it's going to split. And we can figure out how much goes down this branch, how much goes down this branch, and how much goes down this branch by using the current divider. So if we want to use the current divider formula, again, it's on our formula sheet. So we can say that the current through branch A, so there's branch A, is equal to 9 milliamps is the total, so 9 milliamps. This is the branch we concern ourselves with, so that's a 3K branch. And all of this in parallel worked out to be 1K. So 1/3 of 9 is 3 milliamps. We can find the current down branch B, 9 milliamps. The resistance of branch B, 3K. Our total, 1K, 3 milliamps. Kirchhoff's current law says that all currents must add up to the total, so that means the current through branch C is also going to be 3 milliamps in this case. And again, because each branch has a resistance of 3K. If we wanted to find our voltages now, we can use Ohm's law because we know current times resistance is equal to the voltage. So on this first resistor, we've got 1K times, and the current down that branch is 3 milliamps. So this is the voltage. So on this resistor, that voltage would be 3 volts. This one, I have 2K times 3 milliamps, giving me 6 volts. And you can do the same thing for every branch. You know the current going through, and you know the values of the resistors. You can calculate the voltage. You know the current going through and the value of the resistors. You can calculate the voltage. So the trick to solving any of these circuits is to be able to recognize which one of these formulas you can utilize. Again, this one is for series, this one is for parallel. And since we're dealing with series parallel circuits, there's no formula for it. What we need to do is we need to take the series parallel circuit and we need to express it as things in series or things in parallel, not a combination of the two. So in this particular case, it expressed to parallel. In the other case, things were in series. So the bubbles were in series. Here, the bubbles are in parallel. So if you look at it that way, hopefully it makes it a little easier to understand which one of these formulas you can use. So in this case, it's bubble A, bubble B in parallel. So we're using that formula. In this case, bubble A, bubble B, bubble C are in series, and we're using this formula. Once you do that and find I total, you just kind of work your way through the circuit using Ohm's law and any of the other rules and laws that were available to us on the formula sheet. All right, so now what we've got is maximum power transfer. So first of all, let's talk about what is maximum power transfer. So maximum power transfer is if I had a circuit with a voltage and an internal resistance and a load, Maximum power transfer is transferring the maximum amount of power to the load. So from the circuit, maximum power transfer is the ability to maximize the amount of power, not current, not voltage, but the combination giving us power, maximum amount of power that can be delivered to the load for any circuit. In class, we did the whole example about the stereo and the speakers, and we did our calculations based on changing the speaker on the stereo. So the stereo was built, and we were trying to figure out which speaker would be the loudest by calculating the power output of a variety of different speakers. And the one that has the largest amount of power would be maximum power transfer. And we realized that maximum power transfer actually happens at one point and one point only, and that's when the internal source resistance is equal to the load resistance. So maximum power transfer happens at this point, and if we looked at power versus load resistance, you're going to see a graph that kind of looks like this, where here is the maximum power that the system will be putting out, and that happens right at the point where RL is equal to RS. Now, if we were asked to prove maximum power transfer, this is how we would do it. So let's say we were given a circuit like this, and we had RS and RL and 10 volts, and we'll say RS is 1 kilo ohm. And let's say the loads we have 1 kilo ohm load, and we also have RL is equal to 2 kilo ohms. And if the question said, prove mathematically that this happens at maximum power transfer. So basically, we're trying to prove mathematically that when RL equals RS, it's the highest amount of power. So what we would do in this case is we would actually have to calculate the power delivered to each of those loads in that circuit, and whichever one is larger. So in this particular case, we want to find RL, or take RL, we're going to take this 1K and put it in there, and we're going to calculate the power. So we know that power has a bunch of formulas. The most convenient one for us is I squared R. Because it's easy to find the current, because this is a series circuit, so it's easy to find the current, and we know the resistance. So this would be there. So the power of RL is equal to the current through RL times RL. So in this case, RL is 1K. So therefore, this current, so the current is equal to the voltage total, which is 10, divided by the resistance total, which is 2K. It's this one plus this one, because it's 1K resistor and 1K resistor 2K. So that's 10 divided by 2K, and that gives me 5 milliamps. So now I take 5 milliamps squared times 1K. So we got 5 milliamps squared times 1K equals 25. So in this case, power is equal to 5 milliamps squared times 1K, which equals 25 milliwatts. So 25 milliwatts is the power that would be produced here if that resistor was 1K. Now what we're going to do is we're going to swap out this 2K resistor here, and we'll do the same math. So I is equal to V total divided by, and now the R total is 2K plus 1K, so that's 3K. So that's 10 divided by 3K, and that gives us 3.33 milliamps. So now I'm going to apply this formula. Power is equal to 3.33 milliamps squared times 2K, which gives me a power of, so 3.33 milliamps squared times 2K. 22.2 milliwatts. So when we compare the power delivered to the 1K and compared to power delivered to the 2K, it's obvious that this one has a higher power. So between these two resistors, this one had the higher power. And we know that this will become the maximum power transfer point because this resistance equals this resistance. So this is proving mathematically. So when I compare those two numbers, this number is larger than this one. So therefore, maximum power is being achieved here. And it doesn't matter what value of load we put, when we do the calculations, it will always be less than this one. And last on the test, Thevenin's theory. So the idea of Thevenin's theory is to be able to take a complex circuit with a load and simplify it down to represent Thevenin's equivalent circuit that looks like this, where this is V Thevenin, R Thevenin, and RL. So whatever voltage we had and whatever all these resistors were, we would simplify this circuit down to this one. And when we say it's equivalent, what we're referring to is this circuit will provide a certain amount of current to the load. This circuit will provide the same value of current to the load. So when you have the same current through the same resistor, so again this would be the 1K resistor, when you have the same current through the same resistor, you're going to get the same voltage, and you're also going to get the same power. So what that means is the output of this circuit will be exactly the same as the output of this circuit. So think of it as, here's your box. The energy coming out of that box will be the same as the energy coming out of this box. So the trick is how do we create Thevenin's circuit? So we have to calculate two values. there's going to be V Thevenin and R Thevenin. It does not matter which value you calculate first. The two values are completely separate from each other. They have different procedures and have nothing to do with each other. So it doesn't matter what you do first. You can do Thevenin's voltage or Thevenin's resistance. So the procedure for Thevenin's voltage looks like this. We remove the load. And the reason we remove the load from the circuit is because the load is outside of the circuit that we want to simplify. We want to simplify what's inside the box because the box here is going to be equivalent to the box here. The load is outside the box, so we're going to take it away. Remove the load. We're going to mark it with reference points A and B. And then we are going to find the voltage from A to B, and that voltage is, Thevenin's voltage. Thevenin's voltage. And that's it. Thevenin's resistance. Completely different scenario. We're calculating a new value. Its procedure, remove the load. And again, we remove the load because we're trying to simplify what's inside the purple box, and the load is outside that box. So we don't want it in the calculation. So we remove the load. We're going to mark it A, B. Next thing we're going to do is short the source. So we're going to short out the power supply. And with the power supply shorted out, we're going to find the resistance from A to B, and that resistance is Thevenin's resistance. So what we're going to do is I'm going to take this example and we'll walk it step by step now that we have the instructions. So we have 1K, 2K, 3K, 4K, and RL is over here at 1K. And the voltage, we will give 12 volts. So let's find Thevenin's voltage first. And again, it doesn't matter which we do first. We can do the voltage, we can do the current, it doesn't matter. We have to find both. So the first step says remove the load. So what we're going to do is we're going to get rid of the load. So I'm going to get rid of that and I'm going to mark it AB. So the first step is I'm going to be doing this. So here is the circuit. And I've removed the load. I'm going to mark it A and B. So where the load was connected, you mark A and B for reference. And this becomes 1K. 2K, 3K, and 4K. And the voltage was 12 volts. The next step says find the voltage from A to B, and that's Thevenin's voltage. So what we're going to do is we're going to try and find the voltage from A to B in this circuit. So in this particular example, A is here, B is here, so the voltage is going to be across that 4K resistor. Or you can see it's also across that resistor because the two of them are in parallel. But that's the voltage we're looking for. So if we were given that circuit and all we had to do was calculate the voltage across that 4K resistor, should be not a problem. So first thing we want to do is find our total of this circuit, so that we can calculate I total, and then we can see where the current is going. And if we can figure out this current down this branch, we can find out what that voltage is. So there's many ways to solve this. I'm just going to follow the simple current way. So R total, again, this is similar to our example we had at the beginning when we were looking at series parallel. So there's bubble A plus bubble B plus bubble C. So R total is going to be 1K plus 2K plus 3K in parallel with 4K. So 3K in parallel with 4K. So 3K in parallel with 4K. So that goes 3K times 4K divided by 3K plus 4K. And that comes to 1.71K. 1.71K, 1K plus 2K. So that becomes 4.771 kilo ohms. Now, I total, 12 volts, divided by 4.71 kilo ohms. 12 divided by 4.71 kilo equals 2.55, we'll call it 2.55 milliamps. So now we know that the current that's coming up from that power supply, so this, in this circuit, this one, the current is 2.55 milliamps. And we want to find out how much is going down this branch. So we can use that current divider formula, and it says current of the 4K resistor is equal to I total. The 4K resistor is the one we care about. And then this parallel, which is 1.71K. So we care just about this parallel spot, and we care about the split. So in that split, we care about the one branch there. So I total was 2.55 multiplied by 1.71 divided by 4 is 0.4275 times 2.55 milliamps, and that gives me 1.09 milliamps. So the current going through that branch is 1.09 milliamps. So we can use that to calculate the voltage across the 4K resistor is equal to 1.09 milliamps times 4K. So 1.09 milliamps times 4,000 equals 4.36 volts. So 4.36 volts is across that resistor, which is from A to B. So this is V Thevenin. So V Thevenin, in this case, is 4.36 volts. So what we do is we go to our Thevenin circuit and we put in 4.36 volts. So now what we need to do is we need to do Thevenin's resistance. So if we take the same circuit, so it was 12 volts, Here's RL at 1K, 4K, 3K, 2K, 1K. So there's the same circuit. We go back to the beginning, and now we're going to calculate R Thevenin. So first thing we're going to do is we're going to remove the load, mark it AB. So here's the circuit. Here's A, here's B. Remove the load, mark it A and B. The second step says we're going to short the source. So that means what we're going to do is get rid of the power supply and just put a line there. Now with this circuit, so we'll put our values back in. That's 1K, that's 2K, that's 3K, and this is 4K. In this particular case, what we're going to be doing is finding the resistance from A to B in this circuit. So with the source shorted out, we're going to find the resistance from A to B, and that will equal Thevenin's resistance. So in this particular case, when we examine this circuit, we have this branch in parallel with this branch, in parallel with this branch. So this could be branch A, B, and C. And so R Thevenin is equal to 1 over, this is 4K, plus 1 over 3K, plus 1 over 3K. So this is A, B, and C. And if we put that into our calculator, 4K, 1 over, plus 3K, 1 over, plus 3K, 1 over, and 1 over that. 1091. So 1091 ohms. So then we go back to Thevenin's and we put that in as the resistance, 1091 ohms. So following Thevenin's procedures, we have created Thevenin's circuit. Now, these circuits are equivalent with respect to the load. So that means whatever this box sends to the load, this box will send the same to the load. So what we want to do is, in this first case, let's find the current that's going to the load. So current going to the load in this case is V Thevenin divided by R Thevenin plus RL. So all we're doing is calculating the current that's going to be flowing through that circuit. So V Thevenin, that's the voltage, R Thevenin plus RL. So this is 4.36 volts, and this is 1091 ohms plus 1K, which gives me 2.091 kilo ohms. That's silly. Yep. And that's 4.36. So 4.36 volts divided by 2.091 91 kilo ohms gives me 2.09, we'll call it 2.09 milliamps. 2.09 milliamps. So according to this circuit, the current going through that resistor is 2.09 milliamps. Now, if these circuits were equal, we should be able to calculate the current through the load in the original. So here we have to find our total so that we can calculate I total, and then we can figure out what current is going down that branch. So in this case, our total of that circuit, so we've got 1K plus 2K plus 3K in parallel with 4K in parallel with 1K. So we got 3K in parallel with 4K in parallel with 1K is 631.5 ohms, our total. And that makes sense. So that's what this part is. So this it makes sense because 631.5 is less than 1K. That makes sense. So we got 631.5 plus 2K plus 1K. I should have left myself some more room, but that's all right. So we get 3631.5 ohms, our total of this circuit. I total is the voltage. Now, the voltage we gave ourselves was, let's see, 12 volts. So that's 12 volts divided by 3631.5 ohms equals 12 divided by 3631.5 equals 3.3 milliamps. So I total is 3.3 milliamps, so that's what's coming out of there. We will care about what's going down this branch here. So we can use the current divider formula. It says I of the load is equal to I total. We care about what's going down this branch. The resistance of that parallel network is 631.5, which we had from that other calculation. So that becomes I total, which was 3.3 milliamps. 631.5 divided by 1K. So 631.5 divided by 1000 equals times 3.3 milliamps, 2.08. So 2.08 milliamps. So taking into account any rounding errors in our calculation, this current and this current are equal. Therefore, when it comes to looking at the load, 2.08 milliamps, this box puts out the same current to the load as this box. So that means that the two boxes are electrically identical. So that means they put out the same current, same voltage, same power to the same load. So Thevenin's theory is taking a complex circuit like this and simplifying it down to a series circuit with two resistors and a power supply. Being able to calculate it, there's a procedure for Thevenin's voltage and a procedure for Thevenin's resistance. So there are videos on Blackboard that show you examples of different Thevenin calculations. And then on Blackboard there's also a printable procedure for Thevenin's. So it walks you through one example like what we did right here. So again, this is a review for Test 2 Tech 101. 3 major topics: series parallel, maximum power transfer, and Thevenin's theory. Good luck on the test, everybody.